So in the previous class we looked at the common gate LNA, right? Are there any questions about the common gate LNA? Let's quickly review it before we go ahead with the other stuff. So two things we looked at. So first, the noise from a transistor can be larger than 8 kT by 3 gm. Okay, the noise current squared, because this 8 kT by 3 gm is valid channel MOSFET, okay, at low frequencies. At high frequencies for short channel MOSFETs, the noise can be different, okay, and gamma, the effective gamma can be larger than 2/3. Now if you actually see the way noise is modeled for modern short channel MOSFETs, whether it's at low or high frequencies, the way noise is modeled is actually different in the modern files. They can be modeled this way also, flicker noise, thermal noise separately, as well as flicker noise being some 1 over FKF by 1 over F, and thermal noise being 4 kT gamma GM. But there are different ways of modeling also. If you look at the model file, you'll be able to tell. If you go up and read up the documentation of the way, so a lot of these models follow a BSIM, right, which is a standardized way of modeling MOSFETs. So there is BSIM versions, different versions. 2 or BSIM 3 would be something very similar to what you see here. BSIM 4 and so on model things differently. They also have the option of modeling it this way. Okay, but they need not be modeled this way. You just need to remember that in case sometime in the future you go in and look, hey, I expected gamma to be specified, it's not specified, right? Flicker noise, I expect KF to be specified, it's not specified. You need to go back and look at the ways of modeling this. You'll find that there is some flag, noise flag that is set such that this noise is modeled differently. Coming back to the common gate LNA, we knew that the input resistance of a common gate transistor is 1 over GM. So we set that to be equal to 50 ohms. So Z in 1 over GM is 50 ohms. So GM is 20 millisiemens. Okay. The problem is this also comes in parallel with some capacitance. So at low frequencies it will look like a good 50 ohm matching. At higher frequencies it will come with some capacitance. It will have an imaginary part. Of that by adding some inductance to tune out that capacitance, so that you now get a narrow band LNA. The common gate LNA is normally a wide band LNA, but if you go to high frequencies, at low frequencies it's a very good wide band LNA. So for a large range of frequencies it will look like 1 over GM, okay, like a 50 ohm match, until the capacitance, impedance of the capacitance SCGS 1 over SCGS 1 over j omega CGS1 starts mattering. Okay, it becomes significant compared to the real part. Then it becomes mismatched. How does it get mismatched? If you plot the S parameters, the input S11, the input reflection coefficient, find that starts becoming significant. It is supposed to be very small, but it will start being larger and larger. Okay. And as I promised, one of the classes in this week or the next week, I'll cover S parameters. I've covered some link to some notes, okay, but we'll probably cover it in a brief manner in one class. Okay. But I think all of you said you know what reflection coefficient is. So I'm trying to explain it in terms of reflection coefficient. That takes care of the input match. So it is supposed to be a very wide band LNA. If you go to high enough frequencies where capacitance matters, it becomes a narrow, you have to make it a narrow band LNA, but tuning it out with an inductance. What can you do to make it a wide band LNA and push out the point at which the capacitance starts mattering? You have to achieve that 1 over GM1 20 millisiemens with very one, right? Fundamentally that's what we mean. So if you want a wide band common gate LNA, what you mean is What does this mean for us? How do you do this? Small CGS1. CGS1 is directly related to the width of the transistor. The length is going to be minimum length. Okay. So this means small W1 and L1. Okay. This means now you together with this large I bias. Correct? That's what this means. You take a very small transistor, use enough current to get 20 millisiemens GM. You will get a great input match and a wideband amplifier. But now you have a problem. What does this mean? Large I bias, small W. What does that mean? Put these two together. Your current density is extremely low. Taking a very small device, pumping a lot of current. Okay. VD-SAT, VGS are both going to be extremely large. You're making VD-SAT larger and larger by making the device smaller and smaller and increasing the current. Okay. What does this mean? If you have large VD-SAT, what can you guess? You can automatically guess that the linearity of the device is going to be, linearity of the LNA is going to be worse because the swings are now being restricted by using larger and larger VD-SATs. This is for the signal transistor. It's not even for the cascode or the current source or anything like that. This is for the signal transistor. Okay. So this means that most probably somewhere you will have to bias the transistor using large VDS to keep it well in saturation with swings. Okay. So this normally means limited swing. Okay. This normally means limited swings. This does not always mean worse IIP3. Okay. Because IIP3 excuse me, IIP3 looks at very specifically only the third harmonic content. Okay. This one does not always mean worse IIP3, as we'll see. Right. When we finish looking at all the LNAs, we'll probably have half a class saying linearity. We'll never talk about linearity while we are doing design. The reason is because when you are doing design for all, gains, noise figures, etc., you assume that the device is perfectly linear. You assume that the device has square law operation, which means infinite IIP3. There is no limitation on IIP3 is what you assume. Okay. In reality, you will find that there is a limitation on IIP3, which you can unfortunately find only from simulations. There is no hand calculation that you can use to say, hey, you know what, I wanted IIP3 to be minus 10 dBm for my LNA. I need to choose this current and this size. That is just not possible, unfortunately. Okay, because IIP3, okay, at least depends on the third, which we assume for all other analysis to be 0. Okay, so we'll have one class where we'll discuss how to figure out IIP3, how to design for better IIP3. Okay, but now you can see, if you had, let us say, no specific limit on power consumption, you can actually create very wideband LNAs. Okay, as long as you increase voltage supply voltage to take care of the swing limits. Right? You can, in theory, get very wideband LNAs. Okay. Okay. Go back to the common gate LNA. We had one version, okay, where we basically resonated out, I believe, the capacitance of the input transistor and the current source. Now the current source itself will also have drainable capacitance. Okay, I0 is going to be an NMOS transistor. It will have drainable capacitance. All capacitances at the input node are being resonated out by L. Okay. You can also choose to remove I0 and bias the gate of M1 directly with the VGS of M1, which will give you version 2. That also we looked at. Okay. Version 2 has only an inductor at the input node. Okay. To get isolation between input and output, we added the cascode to get more isolation. We added a cascode transistor. The output parasitics we basically out using LD. The load capacitance, drain bulk capacitance of M2, everything we club together as CD. We resonate that out with LD. There will be some parallel resistance RD for the LC tank due to limited Q of LD and CD. Okay. And we figured out how to set those. That will limit the gain of your common gate LNA. Okay. So that is kind of where we stop. Any questions? We also calculated the noise. Any questions on the gain LNA, design of the LNA? Okay. We calculated the noise figure. The noise figure was 1 plus gamma plus 4 RS by RP. Okay. Even if RP was very, very large compared to RS, right? You are designing a very, very high gain LNA. Okay. RP is, 1000 ohms or 2000 ohms. So, 20, 30, 40 times larger than, RS. You will still have a minimum noise figure of 1 plus gamma. If gamma was 2/3, okay, you will get a noise figure of 2.2 dB already. Even for a long channel transistor, you have 2.2 dB. You typically want lower noise figures, 2 dB, 1.8 dB, 1.5 dB and so on. Okay. We want to do better. So that is what we are going to do. Okay. So we will take a slight detour. I suggested one possibility, which was feedback. But we'll come back to the feedback. Feedback was one option. Now, the problem with feedback is that it is less commonly used because, as I pointed out last class, you are intentionally creating a path from input to output. It would have stability problems. So we'll come back to the feedback LNAs a little bit later. Okay. What other options can you think of? So let us go back to the common source LNA. Okay, we didn't do that. We discarded it because you couldn't match the input to 50 ohms because the input was capacitive. Okay, but it turns out that if you take a common source transistor, because you can't, for RF designs, you can't neglect the gate source capacitance. Okay, normally, if the source node, anything happened at the source node, right, the input impedance will still be perfectly infinite at low frequencies. Whatever happened at the source, because you have that insulating oxide between the gate and source, input is assumed to be infinite input impedance. But as you can see, if you actually have a gate source capacitance, if you connect some impedance Z, okay, now the input is not purely capacitive, it is a combination of CGS and Z. That Z could be anything, it could be a resistance, capacitance, inductance, or a combination of all of them. So let us do one thing, let us start by finding out Zin of CGS, Z, and maybe other parameters of this transistor. Okay. So to do that, we will draw the small signal equivalent circuit. So this is VGS. Okay. We'll assume RDS is very large for the purposes of this. We want to find out Zin. Okay. So you apply a test voltage, find out the test current. Okay. please find out what is dt over it. Okay. Correct? Everybody got this? You have three major portions. So you have the input capacitance itself, you have Z itself, and then you will have Z scaled by GM by SCGS. Sorry? Why are we not considering CGD? Because we are assuming CGD, right? What will happen is that if you consider CGD, there will be additional, okay, there are a couple of reasons. What you don't know is that what we have not considered is CGD is quite large compared to CGS. It's about 20-30% of CGS. You already know that you have to add a cascade. We have seen this before, which means CGD will basically go between the gate and drain of the input transistor. It will not, where on the other side you will basically have, we will come to that. The effect of CGD, maybe I need to draw the circuit and explain it. Let me make this point and then come back to why we are neglecting CGD. Because it's hard to talk in the air, I need to draw the circuit and show you. Okay? Just take it for now that CGD will deviate from this analysis slightly when you go to the final circuit. So, this portion is of course capacitive, right? Directly the input capacitance. This portion is Z, whatever you connect at the source side also appears at the input. This one seems to be some product of something that looks capacitive and Z, alright, that is what it looks like. Actually, GM by CGS. What is GM by CGS? Does anybody know this? Huh? Transition frequency. How many of you have heard this term transition frequency? 1, 2, 3. Only 3 people. So now this the transition frequency transistor. 2 pi times ft in gigahertz, where ft is okay. The transition frequency. Now so it's a good thing he brought up CGD, because this is an approximate definition of transition frequency. The actual definition takes into account CGD also, the effect of CGD also. The reason is the transition frequency itself is defined not with respect to GM, CGS, etc. It tells you that the transition frequency for a MOSFET is the frequency at which the current gain of the MOSFET goes to 1. Does a MOSFET have current gain? What is the current gain of a MOSFET at DC at very low frequencies? It's infinite, because the gate is insulating. But we know that at any, we say it's infinite, but it's actually extremely large. That's what we mean. You can always apply an input current. That times the input capacitance will generate a VGS. That times GM will generate an output current. Okay. So, if you to push a current through the gate of a MOSFET, some that will follow. I have a picture. Okay. So you want to find out I out by I in, this frequency in gigahertz, also called the transition frequency. GB, what is the transition frequency? What is VGS? Yes, here I in, right? Yes. What is the output current? I out. Okay. As you can see, I out by I in goes to 1 when at okay, S equals j omega and all that, right? You will find out that omega equals omega t, where omega t is GM by so maybe I'll just write that. What will happen if there is gate drain capacitance? It will just add to CGS, as you can see. Okay. Omega t should be CGD. Okay, that's why I wrote that approximately equal to GM over CGS. Okay. go back to this guy. This is the transition frequency. Okay. So now I need to try out different Zs. Okay. Of course, I can see that there is a Z here. So Z can be a resistance. Correct? That will automatically, if I put a resistance in between source and ground, the transistor, I will get a 50 ohm at the input real part. Of course I will. That's what this is telling you. Okay? Yes. Yes. Well, I have not gone there yet. Yes. But that imaginary part can easily be cancelled by adding a inductance or a capacitance. Of course, once if you find out that any circuit has an imaginary part and a real part of 50 ohms, the easiest thing, we had the same problem when we added a shunt resistance of 50 ohms at the gate. It still had a capacitance. What did we do? We solved that just by building a narrow band LNA where the capacitance was tuned out by the inductance. That is very easy to do. Have a imaginary part is very easy and build a narrow band LNA. And at the end of the day, we would much prefer to build a narrow band LNA which works really well, which has very low noise figure compared to a wide band LNA which is, which is not good enough. Okay. If you set Z is equal to R, okay, you have 1 over j omega CGS plus R plus GMR over. Is it okay? It is GM by SCGS times Z. So you'll get GMR by j omega CGS. Residual capacitance. How do you take care of this? Add an inductance. Okay. This is Zn. So it is a series of ohms plus that inductance. Okay. So in other words, some LG, something like this. Looks okay? Now, this will of course give you an input match, but I'll give you a homework. I want you to find out the noise figure of this LNA. Remember that this 50 ohm resistor is going to add noise, right? So you can now find out, assume that there is a load, cascode transistor load. So this is going to be the homework for today. So now to create an input match, I'll add all the bells and whistles. I'll now call this RS prime, which is equal to RS. Okay, I wanted to calculate the noise figure, gain, etc. of this LNA. So the first thing you can say is that resistance R is going to create noise. Okay, great. So what happens if Z is equal to a capacitor? If you add a capacitance in the source path, so in I'll call that some CS. Okay, what will happen? That's what? This is just our academic interest. Of course, this part is capacitive. What is this part? You can see that it gives you minus Gm by omega squared. It gives you a negative real part at the input. This is not what you wanted, of course. Okay, but this might be useful in certain cases. Okay. If you set the Z to be an inductor Ls, now Zn will be 1 over j omega Cgs plus j omega Ls plus okay. So nice thing about this, you get a capacitive part and an inductive part. Okay, so that part we'll figure out what to do with it. Okay, whether we can do something about it, that will come to. This part gives you Gm by Cgs times Ls, a real part which is approximately omega t times Ls. Okay, Gm by Cgs times Ls, that is the real part. Now this part is good because adding a physical resistance, you are creating a resistive input impedance. That's the good part about this. It's a noiseless input match. That is the biggest advantage of doing matching in the common source amplifier using a source degenerated using a source degeneration with an inductance. Okay, so this can so what that means is that you need to choose Ls and omega t such that omega t times Ls is 50 ohms. Very important, right? That's great. Yes, that is what I am coming to next. Unfortunately, you cannot independently cancel out both the CGS effect and the and set it to 50 ohms. Okay, so setting 50 ohms is your first priority, right? So because you want to create a noiseless input match, so you set omega t times Ls to 50 ohms. Ls and omega t now, exactly. You can have Lg assuming that there is a residual capacitive part. You have to be careful. If you go to a high enough frequency where the resonance between Ls and CGS has happened, okay, so that's quite important. Okay. Now this is of course Gm by CGS. If you choose Gm and CGS and Ls such that this product is Gm by CGS times Ls is 50 ohms, this does not guarantee that 1 over does not not guarantee that the sum of these two will be equal to 0. Okay. So, if J omega CGS is greater than minus J omega LS, there will be a resultant capacitive portion which you can tune out again using another inductor. That will give you the extra degree of freedom that you require to do both input matching and resonance at the same frequency. Okay. Okay, so this part is good. So now our resultant circuit looks like this: LS, LG. Okay. What do we know? Our second design condition is that your desired frequency of operation is 1 over 2 pi root of CGS into LS plus LG. So you choose LG such that this equation is true. Okay. Yes. We are talking about this case. Just 1 minute. Okay. Yes, we had L in series. Resultant capacitance, correct. Why do we have this L in series? For this circuit or for the new circuit? That is exactly what I have explained here. If, remember that the impedance has 3 portions. This portion is the imaginary portion. The other portion is the real portion. How do you know that the portion will be 0? Yeah, so I realized that, that's why I went in and deleted all those LGs. It is just L. You assume some L. Okay, it's confusing. I should not have used LG then. So, since this portion 1 over J omega CGS plus J omega LS may not be 0, you have to set it to 0 by adding another inductance. Now we'll add the bells and whistles. The output of this is the current. Okay. Okay. You may want to bias it separately. So we'll add an infinite capacitance. So far so good. How will you bias this guy? Maybe through a large bias resistance. VB is equal to VGS. So I'll call this VB1, CGS1. Remember that CGD appears between the gate of the transistor and the output node. So you add the cascode to isolate the input and output to make the circuit unilateral. VB2. RD is not something that you add, it is the parallel resistance of the tank. Okay. CD includes load capacitance, drain bulk capacitance of M2, etc. LD is chosen to resonate out the total capacitance at your frequency of interest. Any questions? Yeah. So, if that is not the case, what that means is that the value of LS that you have chosen needs to be modified. And the value of CGS that you have chosen needs to be modified. That is what that is telling you. Okay. So, GM is set by current as well as size. Right? CGS is set only by size. The combination of current and size sets omega T. Okay. Omega T and LS together set the input resistance. You can see this is an under constraint system because your degrees of freedom are current, W over L, right, and LS. Whereas the only constraint is that input impedance needs to be 50. Right. There are various values of omega T's and LSS that if you take a transistor, by choosing different values of W over L and current consumption, you can achieve anywhere from a few megahertz, tens of megahertz to hundreds of gigahertz of FT. If I take a transistor that is millimeters long, millimeters wide, okay, with minimum length, I am assuming minimum length everywhere. If I take a transistor that is millimeters wide and pump in microamps of current, I'll probably get FTs of the order of megahertz, tens of megahertz, maybe even lower than that. I'm taking a very, very large transistor, pumping in a very, very small current. It is most probably going to be operating in subthreshold, not even in the saturation, regular, strong inversion saturation region. You can build LNAs which are operating in the subthreshold region in weak inversion. Okay, they will have very low FTs. It is also possible to choose a very, very small device, lots of current, to get FT to be as large as possible. Remember that capacitance of the device CGS goes linearly with the width. For a given current, GM goes only a square of the width. Okay, so if you choose a very small device, a lot of current, that will give you best FT. Okay, so you can now, based on these two degrees of freedom, you can choose any FT that you want. For that FT, you choose the LS that will give you 50 ohm input impedance. You can clearly see that this is an under constraint system. Okay, what you have to do in case LS ends up being such that it's the total, the sum of CGS impedance and LS impedance ends up being inductive. Okay, you will clearly have to go back and change FT of the device. You need even larger FT, even smaller LS, so that it still looks capacitive in result. Okay, you may think that you can add some capacitance in series and get by with it, but as we will see, it is not so simple. When we analyze this common source LNA next class, you will find that it's not so simple as just adding a capacitance. There are other effects on the gain of the amplifier, which is not so obvious right now. Okay, any other questions? If not, we'll stop here. Okay, in tomorrow's class, we will start with the gain and then noise figure, etc. of this LNA. Okay, so this is the common source LNA, or abbreviated as CS LNA. And we'll find that this one, because of the fact that LS is noiseless input match, plus one more thing which we'll see in tomorrow's class. There are two things which make this a very good LNA, very low noise LNA. So, very popular choice when you want a narrowband LNA with lowest noise figure possible. Yes. Sorry? We will see that in tomorrow's class. Just remind me, once we do the basic analysis, we will see how we can get away with it and whether we want to get away with by making it not depend on CGS or not. Bring this point up in tomorrow's class and we will see. Once you do the analysis of the LNA and look at why it is so good, you will also see that making it independent of CGS will make it bad. By whichever way you do it. Okay? You may think that this is a series resonant network, right? What are the ways in which you can think of not making it depend on CGS1? One point is to add a large cap in parallel with CGS. You could do that. Okay, what else? You could also add a large cap in series. This is after all a series resonant network. You can add a very small cap in series with this to make it depend on the smaller capacitance. Okay? Both of these are bad from the point of view of the advantages of the common source LNA. Both of them will give you suboptimal performance. What we'll do, we will do the basic analysis of this noise gain, noise figure. Then we'll try doing these two things that you suggested. Right? Adding capacitance in parallel with happens. Adding capacitance in series. Change that infinite capacitance to some much smaller capacitance. Okay? Some physical capacitance. We'll also see what that is. Okay?